Good morning, everyone. This is Marc Ballouz, President of ISSMGE, happily starting a new IITT episode. It's the 34th one, so we're almost covering all the technical committees. And this time, it's a really special topic, a rare one. I'm going to share my screen to introduce the speakers. Here we go. So with us, we have the chair of TC219 on system performance of geotechnical structures, Professor Zheng from China, distinguished professor at the University of Tianjin. And I really like the topic, theory without practice is empty. I love that. Professor Kenichi Soga is our second speaker from UC Berkeley, is a member of TC219 System Performance Monitoring and Assessment using emerging sensing technologies, so state-of-the-art presentation. And Professor Anna Zhou from the University of Macau, also member of TC219, spatiotemporal deformation prediction for immersed tunnel in the ocean environment.
Environment.
Again, this is environmental, ocean environmental.
It's
Yeah, second time with us, complementing her previous presentation. Welcome to all of you. I like to give the floor to Professor Zheng to start. The floor is yours.
Okay, I'll share my screen.
Welcome. If you put yourself, the other speakers in mute, unless you have to interact.
Okay, can I start now?
Yes, floor is yours. Go ahead.
Okay. Morning, everyone. I say morning because this is morning in China, so I have to say morning, everyone. I like to take this opportunity and about 15 minutes to briefly introduce system performance of geotechnical structures, which is a theme of TC219. My presentation including two parts. First, I'd like to give a basic introduction of TC219. TC219 was established in 2019, and I'm the chair from China, and the secretary is Professor Guo from Tianjin University. About membership, totally there are 31 memberships. Among them, there are 3 members nominated by TC chair, and the 20 nominated members by national societies, and the 6 corresponding members, and all of them are from 14 countries. Then I'd like to briefly introduce the TC activities between 2022 to 2025. And normally we have 4 major activities. The first one is workshop held in last year, Chinese Academy of Engineering Science, and the Technology Forum, and the 13th International Bridge, and the Tunnel Technology Conference. And the theme 3, Intelligence Construction and Safety of Urban Large-Scale Comprehensive Hub Project. And the second one is workshop held in September last year, which is held in the 2005 Annual Academic Conference of the China Civil Engineering Society, and the same 2019 Forum on AI-empowered system performance of geotechnical engineering. And we held a seminar in 2024 to TC219 seminar series on resilience, evaluation in geotechnical engineering. And Dr. Sotiris gave a presentation from Brunel University of London. And the fourth activities is we have the special session on May 2025. A special session of TC219 was held in Zhou Shanghai 2024 conference. And the last one, we held a webinar in 2022. And the theme is resilience evaluation in geotechnical engineering. And then I'd like to introduce the future activity in 2006. The first one, we are going to organize a TC workshop in Vienna, ISSMGE. The title will be Performance-Based Design in Geotechnical Engineering. And the second one is we are going to organize a TC administrative meeting in Vienna. And the third one is we are going to work with TC 204 to organize a workshop at the University of Cambridge, roughly in November this year. Then I move the second part, and I'd like to briefly discuss what is system performance. And I'd like to raise several questions to briefly give the idea what we think that system performance would be. The first question is soil properties and system performance. And we can see from this figure for a deep excavation returning structure, normally we conduct 2D analysis to see the overturning failure when it will occur. And we have to do model tests with 2D, 3D tests. And we can see in practice, the progressive collapse normally is triggered by local failure. So how do soil properties influence the progressive failure of contiguous returning pile once local failure of piles occurs? My question will focus on, will higher soil strength improve the performance of contiguous returning pile to resist progressive bending failure, especially when the returning pile is designed using the same factor of safety against bending failure? And I say why I raise this question, because one would assume that the better soil, the higher soil strength, the safer would the safety would be higher, and the geotechnical structure will be safer. Is it true? We have conducted model tests under the 3 soil strength conditions to investigate the progressive failure of cantilever returning piles triggered by the initial failure of these 4 piles. And the bending moments were measured immediately after local failure occurred. And we can see from this figure that the highest soil strength provides greater lateral stiffness to the pile, and resulting in a large increase in bending moment. So this means that the pile system becomes more susceptible to progressive failure in much stronger with higher soil strength. And the question 2 is about structural elements and system performance. We can see for this column support embankment, when we conduct global stability analysis, normally the fundamental assumption have been made. One is the rigid columns, all the columns follows a shear failure mode. And the second assumption is the failure of all the columns occurs simultaneously. My question would be, is the contribution of each columns at different locations the same? And will the performance of individual columns influence the overall performance? And we have conducted a centrifuge test and numerical surcharge. And by increasing the surcharge on the face of the embankment, and we check the contribution of each columns by increasing the surcharge to evaluate its contribution to the global stability. And the results here indicated that the contribution of columns on the embankment shoulder is significantly greater than that of the other columns. And we can see here, if we increase the bending strength of each columns, and we can see here, the pile 6, pile 7, pile 9 made no contributions, but the pile 3, 4, and 5 made the most significant contributions.
Professor, so from your presentation,
yes,
you are telling everyone basically, and myself, that the piles or the stone columns or the vertical elements at the shoulder of the embankment should be larger than the middle ones. Is this right? Is this a good recommendation?
Yes. And we think the most reason is that because the contribution of the piles under the shoulders can provide the most significant contribution to prevent the stability failures.
Very nice, thank you.
Okay, I continue. And the next question I would raise is the post-failure behavior and system performance. We can see from these figures, we normally conduct deformation analysis to see is it acceptable in terms of normal use, and we conduct stability analysis to see will it collapse. And my question is, are deformation analysis and stability analysis sufficient enough to ensure the overall performance of column support embankment? And we can see these figures. Actually, the post-failure behavior control is not included in the stability analysis. Therefore, system performance regarding the extent of damage and the difficulty of repair has not been included. So I'd like to take column support embankment as an example to discuss more system performance. And essentially, we have first that like to discuss the progressive failure of columns. We have conducted centrifuge tests and numerical analysis, which indicates that a local column failure may occur during the initial stage, while the embankment can remain stable. And the failure of the critical columns, as shown here beneath the embankment shoulder, may trigger the simultaneous failure of the rest columns, and ultimately leading to the global failure. And also we conduct a centrifuge shaking table test, and it reveals a progressive column failure mechanisms during earthquake. We see here for the lower acceleration at 1.1 gravities, we can see here there is no piles failed. And we increase the acceleration 2.2 G, and we can see here the failure occurs to the piles. And then we increase to 0.3 G, we can see more piles failed. So it's a progressive failure of columns under earthquake. So I'd like to discuss design based on system performance. So we can see here, because these three columns contributes most significantly to the global stability of column supported embankment. So we developed idea sort of a system performance based design or used for column supported embankments. And we compare the two situations. The first three situations. The first one we termed uniform design, with the piles at the different locations at same length, diameter, and strengths. So then we increased the bending strength or fractional strength of three piles and columns, and then we increase all the piles bending strength. So and then we compare these situations. This is the conventional uniform design, and this is the factor of safety of non-uniform designs with three columns being reinforced. And this is the factor of safety of all the six columns being reinforced. We can see here nearly the same factor of safety can be obtained. Then I'd like to discuss the system performance of column supported embankment, the progressive failure of soil arches. We know that soil arches can be built during the backfilling process of embankment. And the previous studies mainly focus on the development of arching effects during backfill of the embankment. And soil arching effects is essential in determining the local sharing between ground and columns. However, we recently found that progressive failure of soil arching can occur when the embankment approach failure. And we have to numerical analysis, and during the backfill of 5-meter high embankment, we can see here the height of the arch can reach 1.7 meters. And then by apply surface load on the top of the embankment, we see the change of the soil archings. And from this figure, we can see here, if we increase the surcharges nearly 40 kilopascals, we can see here the height of the soil arching increased to 2.3 meters. And we continue to increase the surcharges and then found the different situation occurs. For the situation in the center of the embankment, we can see here the height of the soil arching continue to increase, but for the soil arching under the embankment shoulder, we can see here the soil arching became reduced to 0.1 meters. So we can see here as loading increased, soil arching beneath the embankment center continues to develop, whereas the beneath the shoulder degraded after failure of the critical columns. So we consider what it will affect the load sharing between soil and the pile columns. From this figure, we can see here when we increase the surcharge, at the first stage, the soil carried by pile increased, and after surcharge is more than 48 kilopascals, it began to reduce. And at the meantime, the soil carried by ground increased. And from this figure, the right figure, we can see here the change occurred at the moment of the failure of the critical columns under the embankment. We can see here, because the pile spacing between two columns become increased, which induced the degradations of the soil arches. So at this moment, we can see here the pile soil stress ratio reduced very quickly after the failure of critical columns. So can we control the post-failure models and to increase to obtain the better system performance of the column supporting embankment. So currently, embankment design treats deformation and stability separately, and like unified framework for controlling post-failure behavior. And failure evolution is difficult to control once instability is initiated. So post-failure behavior can instead be controlled through a local strengthening. By strengthening weak zones and the critical regions, for example, we install high strength steel rate at these locations, and we are going to check what it will happen. So we control the post-failure mode of these three situations. The first one is without geosynthetic, and the ultimate surcharge is only 52 kilopascals, and we can see that slide face is quite deep and quite big. And then we see these situations with single layer synthetic, and the ultimate surcharge is increased to 68 kilopascals, but we can see here the slide surface is still quite deep. And we can see these situations with two layers of geosynthetic in this location. The ultimate surcharge was increased to 101 kilopascals. And the most importantly, we can see here the slide surface was confined to shallow surface sliding, so that system performance was greatly improved. Finally, I'd like to give a brief conclusions about the system performance in geotechnical engineering. We think there are three aspects of system performance of geotechnical structures. The first one is system safeties, which can including serviceability and normal use, reliability and failure probabilities, and redundancy and adaptabilities, and the robustness and system safety limit state, and the durability and long-term behavior. And the second one is system resilience, which can include residual capacities and the toughness and health monitoring and recovery of function. And the third one, constructabilities, which can include environmental impacts and construction period and industrialized constructions. And finally, I'd like to quote this word given by Marc Ballouz in 1974, to look beyond the provision of resistance to normal loads alone. That's all. Thank you very much. Many thanks for your attention.
Thank you so much. I personally learned a lot about embankment design and optimizing it. You reminded me by analogy when you see pile foundations spread equally under a tower, whereas we should think more of concentrating it under the column loads or the CPRF system. Thank you so much. The floor is yours, Kenichi. Thank you.
Thanks. Yeah, thanks a lot,
My
Professor.
friend.
Yeah. So let me share my screen.
Yes.
Okay. Do you see my screen?
Yeah, perfect.
Okay. All right. So thank you very much for your time and having me here. I'm talking about system performance monitoring assessment using emergent technologies. And Professor Zheng mentioned about system optimization in geotechnical engineering, system performance in geotechnical engineering. I'm going to talk a little bit larger in terms of infrastructure civil engineering, if it's okay with you. Okay,
Wonderful.
so when you look
I've seen your lectures, so I'm looking forward to
assessment of performance of lists, if you look at owners, infrastructure owners, their drivers or uncertainty and risk can be different from engineer like me looking at each component of a civil engineering or geotechnical infrastructure. You can see the uncertainty and risk can be natural hazards, loss in service, third-party damage, stakeholders' expectation, policy, or some sort of a political issues. Whereas as engineer like me, we'll look at a little bit more about life expectancy, risk assessment, risk mitigation, cost-benefit analysis. So we really need to start linking those together. And obviously, if we can showcase what performance of the asset links to a service, and if we prove we can monitor that, then our job is to anticipate what's going to happen in the future so that we can give a projective service performance to our infrastructure owners so that they can reduce the risk of all these things that they face every day as a general manager of a company or the CEO of a company. So what I wanted to do is thinking about that as a system, but excitement is obviously so ISSMGE technical committee members, it's about emerging technologies. And obviously, there are a lot of technologies that we start to embrace, and we're embracing all the time, and that's what technical committees are about. You can see a vertical expectation, vertical axis, the expectation, horizontal axis is the time, and you see always there's a hype of certain technology, and you wanted to bring it to the market. So now you see LiDAR, wireless sensor network, digital image sensing, drones. We all use this nowadays in everyday practice. Of course, it used to be somewhere over here, but we got this technology, and then we have a better understanding of geotechnical infrastructure performance because of these. Obviously, the hype is AI machine learning, and maybe Hana may talk about this, I don't know. But then this is something that we can discuss further on. In terms of sensing technology, you can see computer vision, LiDAR, satellite, fiber optic sensing, wireless sensor network. These are the technology that came in the past 15 years or so, which can measure at the level of 0.1 millimeter, 1 millimeter, 10 to 20 millimeter, which is very important for us to measure, use it to understand the performance of our infrastructure, because we need this accuracy or precision to make engineering decision. And you can do this for many, many locations nowadays, rather than having one single point or multiple few points to make your decision and as engineering. So we have an excitement to get lots of data from our infrastructure. So that leads to more being reactive, from reactive to more proactive. So can we be more proactive? So I just give you one example in our close to our campus. This is the pipeline network of the area that I live. This is our campus. These are the pipeline network for the water. Our water comes from this water treatment plant on the other side of the hill. This is a Berkeley hill, so you have a sort of a shoreline go up to the hill, and the other side is on the 107 meters elevation. Our campus is 109 meters, so every day we have to bring the water up to this 150-meter level to have enough pressure to this particular pink zone. What happened is that we have a big fault called Hayward Fault. That's going to be a big earthquake if it happens, and that crosses some of these important pipelines. So what we have done is, for example, you can have this sort of a fiber optic sensor. I always talk about fiber optics, so bear with me. That fiber optic is a standard optical fiber, but we can measure strain, temperature, vibration at every point along the fiber for many, many kilometers. So I want to go to the details, but thinking about attaching this to your infrastructure, embedding in your piles or slurry walls, and monitor every point along your infrastructure. So that's what we did on this one. This is a pipeline, newly replaced pipeline, which is the HDPE plastic pipe, but we attach the optical fiber on top of the pipeline, as well as we put some trench. These cables can measure both strain and temperature. And we can get the temperature and strain at every point along the fiber for many, many kilometers. Now, this particular location, you can see a Hayward Fault, and this side on the left moves north, and this side of the south moves southwards. On this side moves southward, and typically it moves, this is a creeping fault, so it moves about 4 millimeter per year. I'm not sure you can see, I hope you can see the video of this particular trench and then the plastic HDP pipe where you can see a fiber optics attached, and then we bury the soil. And we keep on monitoring the performance of that, and we can see the actual performance of this pipeline. It's different from having 1 strain gauges or 2 strain gauges. Here you can see the sort of contour of how strain is developing along that line, and you can see with time after 18 months, you can see a small sort of a high concentration of tensile strain developing across the fault. It's very, very small, but you can see, and you can start to see the actual performance of this pipeline affected by the fault movement. And if you know strain, you can integrate to get the sort of a displacement, relative displacement from here. And what you see is a displacement profile, and you can see a larger displacement happening across the fault, about 4 millimeter. So you can see it's a 200 millimeters pipe, and you can see a small movement up even 4 millimeter in a very clear way. We can have a fiber that can measure sound. So we can put a fiber optics to measure sound. So we created a sort of a leakage test. So this is a big leakage, but we can start with a small leakage. I hope you can hear, but let's try. So nothing happening yet. I'm not sure you can hear. Can you hear it? Now it's a big leak. So the point is that obviously you replace your pipe when you see this, but then you can start hearing the sound before it's have a small leak, which you can be more proactive in monitoring. The point I want to think, and coming back to Professor Zheng, is that actual reality is different from what we tend to design. So these are your FE analysis that you may do for your pipeline soil interaction across the fault. We have a big soil tank that will mimic the fault rupture with a pipeline. But in reality, these are great uniform soil, but when you go to the actual site, there are a lot of things. For example, this is a new pipeline replaced pipe, but then if you look at backwards, there's an abandoned pipe. So we don't really replace the pipe, we just keep the abandoned pipe. And the question is that abandoned pipe? We don't have that in the model, but is it going to help the pipe, or is it going to be not going to help the pipe? We don't know. So that's why it's very important to monitor. Once a pipeline is buried, we're not going to see it for the next 100 years. So why not embed intelligence during construction for future generations? I also want to talk about from components, which tend to optimize. We tend to design the optimization, but when you looking at all these components, it becomes a system. It's really appreciating the complexity of our geotechnical engineering and do the right thing. And this is something I want to discuss. So we do a lot of testing on pipeline. This is a structural engineering. So we do a lot of pipeline to test and how and when it breaks. We optimize the joints and all these things. And then you do a lot of simulations like this to see how the pipe is behaving. And then this is a structural analysis. But as a soil mechanics and geotechnical engineering, we do have a soil around. So that means that we have to put a soil around. So that's the soil tank I showed you earlier, where you can put, these are different joints that allows you to relatively move a lot during ground deformation. So it accommodates large ground deformation. And you can see this sort of and then what we do is that we do a fault rupture test. And then looking at the fault rupture and see how the pipe soil interaction happens. Again, it's quite complex because you have a multiple joints. It's not one single joint in your design. It's a multiple joints acting together and then behaving in a very interesting system way. Obviously, when you start to have good joints, that's a good thing. But then when you start looking at actual pipes, there are a lot of things like hydrants, service connections, gaskets, valves that all come together. So in a sense that when you think about system, we have to bring all those together to think about it. So we often tend to design how to design each joint and be perfect, but then we have to understand interaction of all these things, and that's what system level modeling is about, and we're working on that. For example, this is the next test that we may do, is that you see these joints, but also we're going to put hydrants and then hydrant connections and then see how they interact together as a system and trying to figure out where are the weakest points or where are the weakest points so we can understand the system behavior better. I want to finish by saying smart and resilient system from a system to systems. This is not geotechnical engineering, but the point is that when we look at system, there are multiple systems that interacts together. We have a road network. There you have over here bridges and also embankments. We have all these things over here, which we have road network. And then we have a water network, which is related to pipeline or sort of pumps and all these things. And every owner wants to make sure that they optimize on each other, but then there's some interaction that needs to be thinking about. So this is where we want to think about. We are worried about earthquake. When an earthquake happens, what's going to happen to the road or what's going to happen to the water network? So for example, we do a simulation of our Hayward Fault earthquake, where you have a shaking and then every ground condition will be monitored and then modeled, and then we see where the pipeline damage is going to be from the geotechnical analysis. And then we do a water hydraulic simulation. What are the water network and who's not going to get the water? But we don't know where earthquake's going to happen, so we do a lot of Monte Carlo simulations. But also we can link that to red tag buildings or traffic disruption, and this is what system of systems is about. We'll also start to look at how to recover. So again, this is recovery. For example, if you have a building damage, so we do our colleagues from Sim Center do this ground shaking, and then based on the building performance, which building are likely to break, but then at the same time get damaged, but then how do you recover using financing, cleanup, permitting, coming back, and we do this supply demand interaction modeling to understand what are the bottlenecks. And coming back to some interaction of the systems, you can see the water network, you can see the traffic and bridges and tunnels, and you can see the buildings. And this is after an earthquake. We predict for a given earthquake, these may be the damage you may have. But then how do they interact together to recover after 30 days? What are the way it recovers and how do they interact together? And then after 150 days, how do they recover? So again, looking at system of systems, we can start to look at the interaction of different infrastructure systems. So again, geotechnical engineering can contribute to all of these to make sure, but then there are people, owners, who are looking for how this system and systems interact each other. So that's all I wanted to say for today, is to give you a different flavor of system, and hopefully that makes sense to you. Thank you very much for listening.
Little flavor. System of systems. I like it. I have a question regarding the fiber optics. Practical question. So when you install them, different fibers give you different data, not the same fiber, or maybe it can give you two things. And then the data acquisition system, is it fixed and emits data to your phone, for example, or you have to have a team that goes and connects and read on laptops and stuff?
Yeah, you can do many things. Every option is possible. It depends on how committed you are for the instrumentation, and then how much, again, instrumentation becomes an asset that you have to look after. So again, you can do 24/7 if you want to, but then you need to have that box that measures all the time at the site. Or if you're just thinking about, I just need monthly readings to understand the system performance for many years, you can just go one by one. Maybe in the future, robot can do that for us, but it's
Yeah,
just
and is it
monthly.
like for the pipeline you have one monitoring station or data acquisition station is enough, or you need multiple points?
So that's about design. Each box, some box can go to 10-kilometer range. So in
Thank
other
you.
words, it can be multiplexing, so it can spread into two directions, having many lines. So I see some of the
Okay.
colleagues working on road network that crosses 10, 20 kilometers, go back and forth. And then the point is that you just have to make an effort to attach the fiber to your infrastructure and then committed to take readings all the time.
Last question, is it readily available, those fibers, or the special
Yes, yes.
company?
So
Oh,
I think the market is growing. And so we
okay.
started 20 years ago. We were in minority, but then I think it's
I'm
growing.
thinking of countries like Nigeria, Africa, or remote
Ah,
countries where it's funny that you need high monitoring in those countries and then the technology isn't there.
yeah,
So,
no, that's a good point. Obviously, the use of mobile phones, smartphone in Africa is enormously good. And then
oh yeah,
especially in the finance
but
and the
the monitoring using
advising.
fiber optics.
Yeah. And then so that is a question that we all discuss, what's the value? There are other technologies that you can use to monitor many, many things, wireless sensor technology that can across for a large area. But fiber optics, sometimes we are in discussion, we're doing research on using existing fiber that's already being used for telecommunication. And then you borrow one of the line. It's called dark fiber, and you can use one of the line to listen to what's going on. So the water leakage test that I showed you is really, can we use the existing fiber optics that's already being
Nice.
sort of embedded for telecommunication? Can we use it as a sensor? So these may start happen, and there are many
Yeah.
researchers working in that.
I started using INSAR for performance post construction of highways and
Yeah, inside.
nice
Yeah,
presentation. Anna,
yeah.
are you ready? Thank you, Kane.
yes, yes.
The floor is yours.
Now it's okay. The sharing.
Yeah, we can see it.
Yeah, yeah, I can. Yeah, thank you for inviting me to this interactive talk. And I think the TC219 is a great TC. Some of my work, I think everyone is doing in geotech engineering has to deal with the system performance. Even Professor Kenichi gave us a larger view of the system. I think that is true. Geotechnical engineering always do the things not just for our projects, we're actually doing many things for the city. And now we are starting to do connect with the different parties to make more contribution to the city management. And today my topic is about the spatial temporal deformation prediction for the immersed tunnel in the ocean environment. It was a typo in the previous Marc's introductions. I'm sorry about that, but I want to really emphasize this ocean environment, the complexity of the environmental condition of the immersed tunnel. And this is the acknowledgement of the funding. And actually the work we started in 2019, and along the time we already have some students graduated from fresh PhD, and now another 2 students are going with to get doing some progress on this topic. And then also my collaborator from the Hong Kong Zhuhai Macau Bridge Bureau. So firstly, the topic is based on the Hong Kong Zhuhai Macau Bridge immersed tunnel. And it is a tunnel of 6.7 kilometers long. And it is a tunnel that consists of immersed tubes, which is about 180 meters long in general. Let me show the pointer. Okay. And then for each tube, it's composed of 8 segments that is assembled before they are immersed into the sea. And so overall, it's a very long structure as a semi-structure, semi-rigid with joints between the tubes and the segments. Most of the tubes are on the natural foundation. And you can see on the right side, they are in general under 30 meters in elevation, more than 10 meters under the seabed. And then overlying on those sandy soils, CTK, and those medium sand. And on the two sides, we have a different transition in soil improvement method to realize this is smooth transition from the natural foundation to the artificial island on two sides. So for this, in long-term deformation prediction of the immersed tunnel, especially for the intelligent maintenance of the immersed tunnel, is our focus in this topic. Since its first operation in 2018, actually this back siltation is still accumulating. So that is the main driver for the deformation of the tunnel. But of course, there can be also some uneven settlement because post-construction settlement because of the uneven foundation distribution. And in the ocean, it is in the Pearl River Delta, Pearl Delta River region in the Greater Bay Area. So this wave load, there is a daily cycle, and we also frequently have this typhoon season. So you can imagine in this dynamic ocean environment, whether our tunnel is stable or is it static or is it moving? And then we cannot just wait until one day got some leakage problem to look at the deformation. So the deformation prediction is a very important aspect to do, okay, to prevent its larger damage, local damage, or other problems. So this topic is focused on the spatial temporal deformation in immersed tunnel in the ocean environments. So another point is that the tunnel, although it's very long, but in the section, it is 37 meters high. It's like a big hole. So width 37 meters, and then the height is 11 meters. So in the section is still also very large. So we consider it will not be just one-dimensional vertical. It will be horizontal dislocation, differential settlements at the section. Of course, in the opening closure because of the temperature change, and overall along the tunnel because of semi-rigid structure nature. So at the joints, it's expected to have a more deformation, differential deformation. So our solution, as the Professor Kenichi mentioned, we have done some of the work using AI. We call it physics-informed neural network. In this case, only AI cannot work because we just have a very limited data. So we need to utilize more physics mechanism into this analysis to make most use of the data available in the on site. And we do more on the model modernization. And then now currently there's some unpublished work. I will also make a very short introduction. And it's called 3D Geological Information Enhanced PIN. And then I showcase some of the prediction of extreme conditions. So the physical part is that we actually firstly simplify the 7 kilometers long tunnel as a multi-beam model. So for each 180 meters tube, we consider it's an Euler beam on the Vinker foundation. And then the loading is calculated from the surcharge and the backsilting accumulation. And then between the tubes, we have the shear stiffness to simulate the shear force connection. And then with the neural network, or then combined with the physical model, nowadays we call physics-informed neural network, it is quite effective for us to get a solution. It means the inputs of the some monitoring data in the past, and so that we can quickly optimize this parameter, which is the unknowns, like the Vinker foundation modulars along the tunnel, and then to make a prediction. So this actually is not that easy. We found that the results worked, but it's not that perfect. So we consider this, we need to increase the number of the Vinker foundation modulus, because 180 meter under one tube is maybe not enough, considering this large variation of the uneven foundation profile. So if we double all this foundation modulus, it becomes 71, then that also become a problem because of the limited data. So we did optimization. Some of the tube need to consider 2 foundation modulus, some of the tube will consider 1. So this is the Bayesian model class of selection procedure, so that we optimize finally 57 unknown foundation modulus, so that for the red colors tubes, we have 2 unknowns and the other just 1. Then we can achieve a good prediction. This results is for the total settlement prediction and then the joint differential settlement prediction are all both reached a very good R-square value. That is using 5 groups of training data from the 2018 to 2019, and then to predict the results in 2020. Okay, the changes along this time is the backsiltation, as mentioned before. So, but it's not that simple, because the backsiltation at different locations is different, and also the foundation is not that uniform. So and also they will have joints. That joints can adjust the differential settlement of the different tubes. So we consider all these tubes all together in this model. And then certainly with that, we can simulate in the future how this backsiltation will generate further deformation at the different points, and until it reaches a maximum level, right? And that is something we can do in this model. Yeah, as currently our prediction, it will not reach the maximum level until 2030. Right. And of course, there time to time, they also have the measure to release the surcharge, the backsiltation at some location. So we also need a continuous measurement from the echo sounder observation on the field. So in addition, we consider this was not enough, because earlier what we presented is just vertical, right? So as mentioned, it's a very complex, it's a 3-dimensional uneven deformation. So we enhance the model using the more geological information, because under the tunnel, we have more than 300 boreholes that give us a lot of information of the underground soil profiles. So between the boreholes, we can have our model for the soil strata distribution. Then we consider this is a very important information and to be included in the PIN model, that we consider it in one term in the loss function as a low fatality constraint, and then to make a prediction. And in addition, this PIN model can be extended to a 3-dimensional model to consider for each element. We have 8 nodes, and the 4 nodes on the bottom, there is a different foundation modulus. But this one, of course, will generate more unknowns. But at this, in the computational aspects, it's possible we can do it. But in the measurement point of view, actually, we don't have so many measurement points for the 3-dimensional movement. But I will show you some that we have installed on the 2 sides of the tunnel, and then we can see the tunnel as a 3-dimensional deformation. So with this one, we can actually see the tunnel 3-dimensional deformation. One aspect is that the uneven foundation stiffness will lead to a differential deformation. Certainly, as you can see on the left, is just a synthetic case that if even the surcharge, the loading on the 2 tubes, E16, E17 is uniform, but because of the different foundation stiffness of the 2 tunnel, then the differential settlement actually occur on the at the joint and also at different we have the different settlement at the joints and also at the small joints. In this case, we also can simulate. And in addition, we have to notice that the back siltation is not uniform. Before we just consider it is unified. But according to the measurement, echo sounder observation, the back siltation is not, okay, it is especially in the middle part is more concentrated. And then on the south side, the north side is more, so that that will also cause differential deformation of the inverse tunnel. So this one we can certainly predict with our model. And another interesting point I would like to show that is the effect of a wave circle. This tunnel is in the ocean environment. It's in the Pearl Delta River zone. So we have the daily tidal level change. So, and every day in the low tide, the water current is moving this direction from north to south. Then actually that will generate a wave force in general this direction. And then that will cause the tunnel a little bit turned in this way. And then in the high tide is over opposite direction. So we actually in this project we installed our three-dimensional fiber optical sensors that is customized, designed for this immersed tunnel at the 4 points at the two sections. One on the both side, which is the joint section between the immersed tunnel and the buried section, and then that is the part that face up to the seabed and then still in the water. So that is the part that really will face the wave force. And this is an exaggerated demonstration, but in our sensor, we do observe a very small movement in this trend. On the two, sensor 1 and the sensor 4 has this kind of a movement, very, very small, less than 0.5 millimeters. And at the middle is just a minimum, even almost no movement. So with this, our model certainly can do the prediction in the normal period, but we can do more in the extreme condition like a typhoon. This is the typhoon case in 2023. And then we can, from this, our colleagues, they provide us this flow velocity and also the tidal force generated from the flow velocity that can at the location of the tunnel. So the cycle is approximately 26 hours. So at this typhoon condition, significant wave heights will reach to 3 to 4 meters, and the mean tidal level increased by 0.5 meters, and the flow velocity actually increased to 30%. And this is not really the highest typhoon, but it's just a case. We have the results and the monitoring data that show our model can have a well agreement with the measurement. And then, of course, after this one, our tunnel back to the normal state. So it's still within the safe zone, but we can predict in the future or in a more extreme condition or some sunken ship condition, how is the performance in the tunnel. So that comes to my final slides. The conclusion is that we use our PIN model and then extended GI PIN model for the long-term deformation prediction of the immersed tunnel for the case of Hong Kong-Zhuhai-Macau Bridge. And this can realize the spatial temporal deformation at extreme conditions. And in the future, I think it's very important that we do the tunnel deformation and the stress prediction and for the safety assessment of under the complex load condition for the tunnel. And that is all. Thank you.
Thank you so much, Professor. Performance underground tunnel, underwater tunnel. And you're using mainly fiber optics, those L lines, or if you go
Yeah,
back
in
to
my
that
case, the data I show is just
sensor
the
and
sensor.
L.
Yes, for 1 point, actually this is three-dimensional. So we have y is the vertical and x is the horizontal, and the z is the actual
Yeah.
direction. So I don't show that. So you can see a different movement and different direction. So that is because of the
section.
The E
wave force.
sections, the tube or the E section has many tunnel sections connected. Are you monitoring each tunnel section or each tube?
No, yeah, only these two because we do want to monitor more, but at this stage we only monitor the
Capability, yeah.
two. Yeah, and we consider this is two weakest section.
Yes.
Yes.
Okay. Thank you
Professor
so
Yeah, I
Zhou,
much.
may
agree
I ask,
that we should do
Thank
more.
you all.
We should do more and even use the distributed sensor by that the
And
technology
this
introduced.
tunnel, by the way, is open to traffic now, isn't it?
Yeah. Traffic low. Traffic now is open at 24 hours. You can try next time.
Yes.
It's quite good
When I come
experience. Yeah,
visit.
you will not feel any movement, even in the typhoon. Yes.
Nice.
may I ask one question, Professor Zhou?
Yes. Yeah, sure.
Yeah, just this slide. You in this slide you showed that that tide can produce wave force on the right side of the tunnel. So my question is, will this tide produce suction force on the other side of the tunnels?
Yeah, because this we consider this wave force. So that is the tunnel
Yeah.
already up to the seabed. Yeah, it's if the tunnel is in the soil, maybe I'm not sure because the current force will not directly applied to the tunnel, but there could be also water pressure, excess water pressure generated that the small changes a lot in the cycle. We don't have the measurement because the underground soil is clay with sand and silty sand and medium sand. On the two sides, the soil improvement method mostly is the sand compaction pile. So it actually has a good drainage path. So we don't have the monitoring data, so we don't know. But we expect for the other tunnel sections, we will have a less influence by the wave. Yeah, tidal force. Yeah.
Thank you.
Now the entry and the exit of the tunnel, they cross in the water. Why didn't they stay within the soil?
At the
Thinking out
end,
loud.
there are two. This is the old Hong Kong Zhuhai Macau Bridge. Can you still see my slides?
Yes, yes.
Okay. So this is a whole Hong Kong Zhuhai Macau Bridge, and then there are two artificial islands in the sea, and then
Yes.
there's a two bridges. Actually, the bridges connect to the Hong Kong
Above
and the
water.
Macau. Yes, and then
Yeah.
above water,
Then you
and then the
enter.
tunnel enter into from the bridge, from the island into the sea. That is for the large ship to go
cross,
through
yeah.
and cross the this tunnel, and also this is the location that near to the airport. So there is a height limit for the So we cannot do the bridge too high. Then the tunnel is the option.
Yeah, my question is, at some point the tunnel is in the water, so you have water left and right, and then it goes
Yes,
underground.
that is right. That is right. Actually, only the one only this is 33. As you can see, this is the 180 meters. Then the end of this tube is almost up to the seabed. You know,
That's, I think, a
so it's
critical area.
about 200 meters. It goes to the sea, or in going to the sea. Yeah, and then in the middle part of the tunnel, it's deep buried. It's up to the 10 meters under the seabed. Yeah.
Thank you so much.
Thank
Interesting.
you.
I will visit and go through it.
Thank you.
Thank you all for this great episode. Sorry it took a little bit more time, but it was interesting. I think I'm going to be waiting for the next president to give this next lecture on performance TC219 because one episode isn't enough. We'd cover all the structure, infrastructure monitoring, and performance. We really need more than one episode. I wish I had more time. I would have given it another period with covering more structures. But anyways, that's what it is. We'll see the next president. So the idea of ITT is to bring together people from industry practice, young, renowned, and cover as much subspecialties as possible in geotechnical engineering and cover all the technical committees. And in one term, try to do that within the term and then wait, next president will do again. So hopefully this IITT series will continue. Thanks again to all of you and hope to see you soon in Vienna to say goodbye
Thank
to the
you.
president.
Thank you. Thank you. I'm very honored to have the chance at the last to join this ITT. Yes. Thank
You
you.
made it.
Yes.
Ciao, ciao.
Yeah. Ciao.
Thank
Bye.
you. Thanks,
Bye.
everyone.
Okay,
Thank
see
you,
you
Buddha.
in Vienna.
Yeah, yeah.
Yes.